So this project is about explaining the right part of Pluto's heart, so the region that we call East Tomboregio. It's still a work in progress, but I'll present to you what we have so far. So I'll start with what we know. We know that outside the equatorial region, Pluto has distinct latitudinal variation patterns with so bands of nitrogen ice. The North Pole is mostly methane-rich ice. But in the equatorial regions, you have much more diverse terrains, much more diversity, with Cthulhu, as you know, Sputnik, East Tomboregio, and the bladed terrains. So regarding nitrogen ice, we know that nitrogen ice accumulates at low altitude. It's dictated by the solid-gas equilibrium. And we end up with a permanent reservoir of nitrogen ice inside Sputnik planitia. And in fact, we also modeled nitrogen ice deposit outside Sputnik planitia. And we know also that some nitrogen ice deposits can be stable outside Sputnik, but also at low altitude in equatorial regions. Regarding methane ice, there are two types of methane-rich deposits in the equatorial regions. Nitrogen frost that coats mountain tops and crater rims and walls, and the bladed terrains that we mentioned earlier. So now we have this picture of the equatorial region with the diversity I mentioned. Cthulhu, which is relatively volatile-free, Sputnik, East Tomboregio, and the bladed terrains. And I want to talk to you about East Tomboregio, because we are not sure to understand why we have a bright region here. So let's see what's inside East Tomboregio. So this is a geologic map from Oliver, and the East Tomboregio is here, and basically they described it as a low elevation expanse of bladed materials experiencing deposition with nitrogen-rich founding depressions and methane-rich frost, primarily at the pits, ridge, and walls. Okay, so actually this is consistent with the composition maps from Bernard Schmidt. You see here nitrogen-rich ice, mostly in the local depressions, nitrogen bonding, and everywhere else it's methane-rich ice. If we look at the topography, it's not really a low altitude region, but it's not a high altitude as the bladed terrain region either. So it's somewhere in between, and it is comparable to some of the region Cthulhu. If we look at the albedo now, so the key thing is that East Tomboregio is very bright as Sputnik, basically. And it really contrasts with bladed terrains deposit, which are also methane-rich, but much darker, with albedo less than 0.6, whereas East Tombo has an albedo almost up to 1. Okay, so the main science question: why would East Tomboregio be currently dominated by methane-rich condensation, whereas the methane-rich bladed terrains that we see seem to be dominated by sublimation? And why, if methane accumulates as frost in the equatorial region, why is Cthulhu depleted in methane ice? So we want to know more about that, and also why what controls the location of the local bright deposits of methane. Is there a topography effect, an atmospheric effect, albedo feedback effect, and so on? So I start with an animation. It's going to be a movie. I'm going to activate it. But so it's a movie that describes the simulation that we performed with a volatile transport model. On top left here, you see a map showing the initial distribution of methane ice. So we place methane ice as mantles at high latitude, and also in the bladed terrains. Okay? So it's a permanent reservoir of methane ice. And here you will see the amount of atmospheric methane. Okay. And on the right, in red here, you have the surface pressure over 1 Pluto year. So you see that in 2015, we are more or less at 1 Pascal. This is what the model gives us. It's not always perfectly, not always a perfect match with observation, but it's just to have an idea. And in green here, it's the global mean amount of methane in the atmosphere. But most interesting will be this figure, which shows you in green the amount of methane in the atmosphere above East Tombaugh region and the accumulation of methane ice in Tombaugh region, in East Tombaugh region. So when I activate the movie, it will be a little bit fast, but so we simulate several Pluto years, and basically what you see is that methane frost form in the equatorial region, mostly in Sputnik, okay, it's a cold trap, and near the Mediterranean, and in particular in East Tombaugh region. What's key here is that we can look at which seasons methane ice actually accumulates. So it's mostly in northern spring and in northern winter when you have large amount of methane in the atmosphere, which is placed in the atmosphere due to the source of methane that gets activated with the insulation. So of course here the results that, so this is the map we obtained after 3 Pluto years. The results that we have methane frost in East Tombaugh region was expected because we implemented the albedo map in the model. So the East Tombaugh is bright, and therefore it's cold, and it's an albedo feedback, and we form the deposit. But it has been shown by Alisa Earle et al. That albedo feedback are very powerful in the equatorial region, and here it's just another way to show it. Once you have a bright region, it will favor deposition of methane, and it will continue to maintain the region as bright with a larger amounts of methane. So now to know more about the region, we need to do a field trip to Pigafetta-Montes, because in this region, we published a paper a few years ago which describes how you can form methane frost on top of the mountain. So we have the equation that controls the methane condensation sublimation rates on the surface. It depends on the near surface horizontal winds and the difference between the methane atmosphere mixing ratio and the mixing ratio at saturation. And basically, we showed that you can form methane frost on top of these mountains because you tend to have more gaseous methane at altitude. This is what this plot shows. It's altitude versus longitude. And you see that at 4-kilometer altitude, the global climate model predicts an atmosphere layer enriched in gaseous methane. So basically, the mountains peak into this enriched layer. And also, you have stronger winds, usually on the mountains and on the slopes. So this is what this figure shows. It's a map of the Pigafetta-Montes region. And you have strong winds near the mountains. And this favors the mixing of methane molecules near the surface, and therefore favors the condensation rate. And also, you have also the albedo feedback, of course. So in the end, in this paper, we showed that we are able to form frost here on the mountains and not on the western part of this mountain, which is Pluto region, for the following region. This sketch actually summarizes the findings that the mountains peak into the warm methane-rich atmosphere. And you tend to have mountains resembling Earth's snow-capped mountains, but not for the same reason, actually. So back to the simulation that produced this result. This is another movie. It shows the altitude versus longitude. You see here the westward winds predicted by the model. You have a Cthulhu region, East Tombaugh region, bladed terrains are here. And what we found is that you have a strong upward winds on the western side of Sputnik and downward winds on the eastern side of Sputnik due to the topography. It's due to orographic waves, but this deserves more investigation. But anyway, when we activate the methane cycle, you see that methane sublimates from the bladed terrains, is transported westward, and the fact that East Tombaugh is really close to the bladed terrain and the fact that you have downward winds here, you will tend to have an enrichment in atmospheric methane in these regions, whereas you can see that in Cthulhu, you have almost no methane that reach the surface of Cthulhu. So when we look at this, but in terms of a map, this is the average methane mixing ratio we get in the atmosphere near the surface in 2015. And you see that in East Tombaugh, you have much more gaseous methane on the eastern side of Sputnik compared to the western side. And in the end, this is what explains the difference between East Tombeau and Cthulhu. In fact, if we do the simulation and where we start with absolutely no frost of methane in East Tombeau, after a few years, you tend to have methane frost in this region and not in Cthulhu. And also, the argument is not excellent with observation, but here, of course, we just try what we get in 2015. We will need to do the simulation over an entire Pluto year to really see if we can form a dark and bright region in this area. But when we look into details, we find that the reasons why you have methane accumulation in East Tombeau are the same than why you get methane frost in Pigafetta-Montes. So the field trip was a good field trip. And it's because you have accumulation at altitude, and also it's also controlled by the local winds. So this is conclusions. So we think we understand why we have deposition in East Tombeau and not in Cthulhu. So it's due to the circulation, the fact that you have a proximity to the blade terrain, an enrichment of gaseous methane. You still have accumulation at altitude of methane and less at low altitude. So if we imagine that if we expand this over time, we will tend to form bladed terrains maybe. And I think this is what we see and what Oliver sees in his geologic maps. It's a baby bladed terrains that are starting to be formed in East Tombeau. And of course, this is to be continued with simulations over long-term periods. Thank you.
Here we go. We've got 3 minutes for questions, if anyone has any.
Leslie Young, Southwest Research. Always great to see your talks. When we first saw the far side of Pluto and what people sometimes called the brass knuckles, my first thought was, boy, is that a wave-induced effect? Yes. What's your J number for your waves? Do you think that this could be causing what we're seeing on the far side?
So you're talking about the transport of methane, this type of animation?
Well, so when you say orographic waves,
orographic waves.
Yes, do you think we would have orographic waves affecting deposition on the far side to make something like the brass knuckles?
Maybe. The truth is that we didn't investigate much the orographic waves yet. It's a project, but we haven't explored very much the wave in the GCM. In fact, we feel that we need a higher resolution model, with higher spatial and vertical resolution. And this is a work in progress. So hopefully in a few months, maybe, because we are building this model, and there will be a talk by Aurélien Falco about it later today or tomorrow. Hopefully we will be able to answer to you in more details very soon.
Hi, Tanguy. Elliot Young, Southwest Research Institute. I've got 2 questions, so why don't you pick the one that you think is more interesting? The first one is, I loved your movie of showing the availability of atmospheric CH4 during a year, but I noticed that there wasn't much in the way of latitudinal transport, and I was wondering if that is consistent with your ideas of some kind of half a Hadley cell on Pluto. The second question, which may be interesting, is the deposition rate. You pointed out deposition rate of methane depends on the difference between the ambient pressure and the vapor pressure. And you talked about there being more methane at altitude, but I wonder if that vapor pressure is such a steep function of temperature that it could be dominated by changes in temperature at the mountaintops from some other cause.
Okay, so for the first question, I think you mentioned that here, just to be clear, there is still a cycle of methane at all latitude. It's just that you don't see changes on the mantles on bladed terrains because the color bar is saturated here, but you still like sublime and condense everywhere. And for the second question, I think what you're saying is that it's not clear how the condensation at altitude could be impacted by the vertical profile of methane and temperature. That's right. For us, it's true that in the model, it's a strong effect on very robust everywhere. As soon as you have a mountain that peaks into the atmosphere at 4 or 5 kilometer altitude, since you tend to have more methane at altitude because of the diffusion of methane in the end, you tend to form frost at altitude very easily. So I would say something relatively robust there.
All right, we do have to move on to our next speaker.